Good afternoon, and welcome to today's session on quantum computing. Last week, we discussed complex numbers and complex vector spaces, which are the foundation of what we will do in the remainder of this course. So I hope you had enough time for the revision and study of the new concepts, especially the ones around complex vector spaces. What we want to do in this course is advance to Chapter 5, Architecture, in which we will look into the fundamental operations a quantum computer can do, like a classic computer has not and or gates. There will be certain gates in a quantum computer, and we will describe these gates in terms of, or these operations, we will describe this in terms of complex linear algebra. But in order to do this, we first need to explore systems today. And after we have explored systems, we will do next week quantum theories, or in about 2 weeks' time, hopefully, we'll be able to start with computations. And quantum theory is something we'll discuss next week in greater detail. But today, we're evolving there step by step. Concretely, we will look first into deterministic systems, and then we will move to probabilistic systems, so systems that will get more complex. And our goal is actually describing quantum systems, but starting directly with quantum systems is a little bit tricky. So we rather look into probabilistic systems first. And in order to understand probabilistic systems, we need deterministic systems. And we'll use plenty of linear algebra for deterministic systems and probabilistic systems, and then complex linear algebra for quantum systems, and eventually we will see how we can assemble such systems together. Now, why is this relevant in a few weeks' time from a computational perspective? So a very simple system could be just one qubit in our quantum computer, and we want to manipulate the qubit. But we could also have systems that are composed of multiple qubits for which we assemble single systems into a larger one. And so today we're not looking into qubits yet. That's something we will see in 2 weeks when we look into architecture, but we will look more into generic systems and become more complex step by step. And this will help us to apply last week's math and then move slowly to quantum today. And next week, we discuss quantum mechanics in greater detail. So if you look into literature for or on quantum computing, you will see that a lot of the literature is written for physicists. Now, most of you don't have a big background in physics. I'm a computer scientist as well. I'm not a physicist. So a lot of the literature will be a bit difficult for us to study. But since I use the book provided, or the course book I have mentioned a few times, Quantum Computing for Computer Scientists, that book uses a different approach to study these concepts. And we will discuss these concepts in terms of graphs and matrices. So we'll have a graph, which we can also represent as a matrix, and discuss all of this step by step. So we will heavily use graphs and matrices to describe these concepts. And with them, we can express our quantum mechanical ideas step by step, as you will see. And we're starting with deterministic systems. Now, this would be a sample system that we are starting with, and we will see that we can describe all of this in terms of vectors and matrices, and I will develop this concept with you now step by step on the whiteboard. Just wait a second for me to switch. So the concepts that are in the slides, I'll develop them with you now step by step. So we are looking into deterministic systems. And this deterministic system we will describe as a graph, but we will also be able later to describe the transitions as a matrix. And we will have multiple so-called positions in here. So we'll have position 0, position 1, position 2, position 3, position 4, and position 5. Then we will have this system in a concrete state where we have values in these positions. And it's all deterministic. And for now, we use integers. Later, we will use probabilities. And then we use complex numbers as we evolve. But we're just starting with the simplest one possible. So we could say we have our system now in a concrete state. And one way we can think about this is that we actually have marbles in each position. And what we want to do is when we evolve this system from one state to another, we move marbles from one position to some other one. But the exact transitions will come later. We can say in here now, we could have 6 marbles in position 0, 2 marbles in position 1, 1 marble in position 2, 5 marbles in position 3, 3 marbles in position 4, and 10 marbles in position 5. And we can describe that state in which this system is as a vector. So we could say position 0 has 6 entries, the next position has 2 entries, the next position has 1 entry or has 1 marble, then 5 marbles, 3 marbles, and 10 marbles. So this is our vector. What we will later see just in order to use the space as efficiently as possible, we will sometimes use row vectors to describe this. So here we have a column vector where all the entries are in one column. However, we can also describe this simply as a row vector. And in a row vector, it's just one row. So we have 6, 2, 1, 5, 3, and 10. But later, for reasons that you will see, we always want our state vectors to be column vectors. And the operations we do, they rely on that they are column vectors. So I cannot just write this as a row vector, but I can write this as a row vector that I would transpose. So always use column vectors. If you use a row vector, which we will do multiple times, we still need to transpose that row vector. So we're actually working with a column vector. Are you fine? Are you okay with that distinction? So we don't mix up column and row vectors. Maybe just send me a signal that this is clear. Otherwise, the operations that we're using, they will not work. And we will use this throughout this course, also when we think about quantum systems, quantum operations, and a quantum computer. We will usually stay with that kind of definition. Now we want to add some dynamics in that system. So we can move from, because now we have an initial state and we want to move from one state to another. So we can think about dynamics that I just defined now. We can say, for example, we move the marbles from position 6 to, the marbles from position 0 to position 5. The marbles from position 1 to position 2. From 2, we move to 4. In 5, we keep them. And from position 4, we move to 5 as well. And from 5, we moved to 2. This could be one example graph that the book uses in one example. And this is a deterministic transition that we will have. So it's very important that we only have if you see this as a graph, we have these vertices or nodes, which would be, this would be one node or vertex, and the other ones. So just in green to highlight, in green, I'm highlighting the vertices or nodes, just two synonyms. And I have these outgoing edges here in red. And it's very important, since it's a deterministic system, that every node or vertex has exactly one outgoing edge. So 0 has one outgoing one, 1 has an outgoing one, 2 has an outgoing, 3 has also outgoing, but it would just stay in here from 4 to 5. 5 has multiple incoming ones. That's absolutely fine. You can have multiple incoming ones, but exactly one outgoing one. Do you all feel okay with graph theory? Maybe just signal um, with red or green, green for yes, red for no. So most seem familiar with that. And do you know what we would name this element in here? Well, maybe not in blue, but in yellow, where I said that in the dynamics, we would have just the edge is outgoing on position 3 and ingoing in position 3. Do you know what we would call this red transition here from graph theory? If you remember the terminology, maybe just send it to the chat. So this red one here, we call this a loop. We also just got it in the chat. So this would be called a loop. So we have an outgoing one in position 3, which is also ingoing there. So in terms of the dynamics, the marbles would just stay there. So what are these dynamics useful for now? What you need to imagine is we will think now in so-called time clicks. So we have our state in one, or we have our state at one point in time. And now we move this forward by one time click into the future. And in terms of these marbles, we would move all marbles from one position to the one where they're going. So these 6 entries in 0, they would be going all to 5. The ones from 1, these 2 entries would all be going into 2. This one entry that is in 2 would go into 4. Everything from 4 would go to 5, and everything that is in 5 would move to 2. So 2 has 2 incoming ones from 1 and 5. 5 has 2 incoming ones from 0 and 4, and so forth. So we move all of these marbles from one time click to another, not just some, and it's deterministic. So this is fairly easy to think about. Now, these are the dynamics. And the interesting thing is we can describe these dynamics in terms of a matrix. So we have our state X, for which we have these marbles, and we can describe now the dynamics as a matrix. And then it will turn out that we can do these dynamics super easy by just doing linear algebra. So our matrix M will be a 6 times 6 matrix, because we have 6 positions, which are 0 to 5. We now need to model how we can move between these positions. And we're using a notation, and that notation is very important that we keep using them and not just the other way around. So the first row of matrix M will describe from which nodes our node 0 has incoming edges. but 0 has no incoming edges. So all the entries in the first row are 0. It's not about the outgoing edges, but the ingoing edges. Now, position 1 also has no incoming edges, so it would also all be 0. Position 2 has two incoming ones, one from position 1 and one from position 5. What we can add here on top are some comments. So we could say this column here refers to position 0, this refers to position 1, this refers to position 2, 3, 4, 5. And for these rows, we could also add comments that this row refers to the position 0, position 1, 2, 3, 4, and 5. Now, since position 0 and 1 have no incoming edges, we will now look into the third row, which refers to position 2. And this one has incoming edges from 1 and 5. So we put a 1 here because it comes from 1 and it comes from 5. So we put another 1 there. And all the other entries are 0. Now, what do you think would the next row look like for position 3, where we only have this loop? If you have any suggestions, just send this to the chat, what that next row would look like. And the answers we got so far, they look fine. So no incoming ones from 0, 1, and 2, but we have this loop in 3, which is this 1 here, and then remaining zeros. For position 4, we have 0, 0, then a 1, because 4 has an incoming one from 2, and the remaining ones are also 0. And now I want to see from you what you think the last row of this matrix could be, which is about position 5, which has incoming edges from position 0 and 4. And you can share this in the chat as well. So we have a 1, do this in red, because it's incoming from 0, and then 5 has an incoming one from 4, which is the other one here, and then all the other entries are 0. So with matrix M, we can describe the dynamics. So just highlight this here. Dynamics is described by M, and X would be describing a concrete state in which we have our system. For some reason, the screen share just terminated. I don't know why. We'll resume it very quickly. So this is our matrix. You will also find all of this in the slides, well formatted with a couple of comments, what I've said orally. Now, what I want to do is I want to do one time click into the future. So I want to move from state X one time click in the future by moving these marbles around. And it turns out this can be described super well using these linear algebra structures. We will have matrix M, and from the right, we are multiplying our state X. And it's very important you do it in this order and not in the other order. We will later see what happens if you multiply the state from the left. We will see what would happen then, but this will come later. What I also want to highlight, usually, say in my other courses, I prefer to have a bold uppercase character like M in bold to describe a matrix and a lowercase character in bold for a state. So we would have in bold a small x. That's typically the convention I use. But in the book, we simply have M and X uppercase, both for a matrix as well as a state. It's not the convention I like, but I'm using simply the one from the book since most of these chapters are to some extent based on the book. Um, so we have our matrix M, which describes the dynamics, and we multiply from the right our state X, and then we do one transition by one time click in the future. Let's try it out. So I'm just copy pasting the matrix from before. We'll do this slowly, step by step, so we're all on the same page, what we're doing. So if I by accident maybe sometime miss a 1 or a 0, this may sometimes happen in a live demo. Maybe just ping me. If you see that I missed something in the slides, it's all well formatted and probably no typos if you want to see it well formatted. So this is my matrix M, and I multiply from the right my state X, which we said is 6, 2, 1, 5, 3, 10. Now we want to multiply from the right, and we see the first row of the result is simply 0 because all of these are 0, and then if I multiply element-wise, I will just get a 0. It's the same for the second row, so we'll have a 0 there as well. And if we multiply now with the third row, this column here, we have a 1 here and a 1 there. So 2 times 1 plus 1 times 10, which will give us a 12. Next one we can try is the next row where we have this 1 here and we have the corresponding 5. That means we get a 5 here. And I want you to quickly multiply the last two rows with that vector and tell me the remaining two entries I need in my vector and send them to the chat, please. And it's correct, it's 1 and 9. Because we had this 1 here and then the corresponding 1 there, and then this one and this one, so it's a 6 and a 3. So, and we can call this for now, for example, y. So we have transitioned from state x to state y by doing this dynamics. If you try it out manually, you would also see that we get the result. That we obviously wouldn't have anything left in position 0 and 1 because they have no incoming edges. In 3, everything would stay. And in this area, we would have some more complex dynamics. But the good thing is we can model this fairly easy with linear algebra. And it turns out a lot of stuff you have seen in, for example, the introduction to Boolean logic and AND gates, NOT gates, OR gates, all of this could also be described in terms of matrices and vectors. And that's something we'll do in a few weeks. And then formalize this and then amend this for quantum mechanical operations. So This was the beginning of deterministic systems, and there are a couple of notes in the slides that um, we will look at later. Everything I've said so far is here in the slides as well. And something interesting will happen now. Say I have my state Y, and I want to do one more time click from Y to Z, for example. So I want to say my state Z would be M times Y, because Y I got up here, and now I want to do one more time click. We could do this manually again, but we could do this also in a different way. For example, since we had our Y, which was one time click from X using the dynamics, we could also say our Y was, well, I'll use different colors just to make this maybe more obvious. And Y was M times X. And now I can think about M times M, so that I multiply the matrix M with itself. So I could say this is M squared times my X, and this is how I get my Z. Since you have all done matrix multiplications, you could now try out for yourself M times M and provide us with the results, but we've practiced this last week. So I will switch directly to the slides to show you this. And feel free to do the matrix multiplication of M with itself as an extra practice. And there's a question here, M remains the same for all the clicks, because M is the dynamics, and the dynamics will not change of this system. What will just change are states. So we have our matrix M from before. We've seen these dynamics, and now we could multiply M with itself, and eventually you would get M squared, which is M multiplied with itself. What is quite obvious here is that the first two rows don't change because there's just everything would be moved out. You have this loop here, and down here there are in rows 3, 5, and 6. There are obviously some changes because you move around the stuff here. So this matrix M squared just means I could now have M squared and multiply from the right my original vector X, and what I would get as a result is 2 time clicks into the future. So I don't need to first multiply X with M, which is Y, and then Y from the right with M, but rather I could calculate M squared and multiply X directly from the right with M squared, and then I would move directly by 2 time clicks into the future. Is this something that makes sense to you? If so, maybe just signal this to me with some reaction. Looks all good. There are a few slides we didn't look at, but I've developed all of this with you. So I had shown you this matrix M for this system, or for this transition. Then here's a more formal definition. If you look at an entry ij, so index I for the row, index j for the column, this is one. If there is a vertex from j to I, we've seen this. I've explained this step by step to you, how we built these rows and columns. It's also one if there's a path of length 1 from j to 1, because these paths, so one edge is obviously a path of length 1. So it's just a more formal definition. We've multiplied here m with x, and it's very important we always multiply x from the right. We will later see what happens if we multiply from the left, but we need to pay attention to something else then as well. And we got our y, and here's also a more formal definition of what m squared would be. The entries are 1 if and only if there's a path of length 2 from j to I. And we can generalize this and say m to the power of k if there's a path of length k from j to I. So you could do this step by step and look at a graph and try to build these matrices, or rather you just multiply the matrices with each other. So m with itself, or you could say k is 3, so you would multiply m with itself again with itself, and you would get m cubed. But here are more formal definitions in case you wish. And feel free to multiply m with itself in order to get this matrix. And you can test then and see you would get the same result if you multiply x with m squared, then first x with m, which is y, and then y with m. And very importantly, always multiply the state vector from the right and put the matrix for the transition to the left. So these are deterministic systems, which we just started to motivate this. And what you saw is it's just eventually we look into graphs and we can describe these graphs in terms of linear algebra, and we have our dynamics. Now we will advance and look into more complex systems. And our goal today is to model quantum systems. And we are now looking into an intermediary step, which is probabilistic systems. So far, these were deterministic systems. And what we saw is we have a certain number of marbles we move around. We don't think about marbles anymore, but rather we will generalize this now and think in terms of probabilities. So we will later need quantum mechanics, and quantum mechanics is a generalization of probability law. But rather than thinking about multiple marbles, we now think we work exactly with one single marble in our system. And if we have a single marble that we move around here, and it's a non-deterministic system, we will have in our state entries actually probabilities. So if we think about a probabilistic system like this, where we don't have multiple marbles, but rather one, and it's non-deterministic, we can move around. And what we will have as entries in here is not a number of marbles, but rather a probability of where that marble could be in. So how likely it is, or how probable it is that that marble is in that specific vertex or node. And we will now think about probabilistic states, and we just look at a simpler system now for which we just have 3 positions. So we have a state vector x, which is still a column vector, but I often use in the slides just a row vector notation. That's why it's very important we transpose the row vector. So that's actually we deal with a column vector. And for a simpler system, we would see here the first entry is 1/5, then 3 divided by 10 and a half. So this is 0.2, 0.3, and 0.5. So it is very important that we have a valid probabilistic state, that all of these entries, they add up to 1. And what they mean is there is a 20%, so 1/5 chance that the marble is in position 0, a 30% chance the marble is in position 1, or a 50% chance that the marble is in position or vertex or node, whatever, 2. Are you okay with that definition of a probabilistic state? Maybe just confirm. Okay, very good. There will be now, because a simpler system, so we only work with graphs that, or for a while now, that have 3 nodes or 3 vertices. And I will again develop all of this with you on the whiteboard. So, probabilistic systems. And these probabilistic systems, they are more complex, and they also allow us that a node or vertex has multiple outgoing edges. So not just exactly one outgoing edge, but multiple outgoing ones are possible because we're now dealing with a stochastic or non-deterministic system. And for this, we will have position 0. And we don't put in now a certain number of marbles because it's just about one marble and we want to know its probability to move around or where it is. And so we have position 0, 1, and 2. And we can now think about certain dynamics. For example, we say, and this is again an example from the book, we can say there is a 1/3 probability that the marble moved from 0 to 1. There is a 2/3 probability that the marble moves from 0 to 2. Then if we look at position 1, we can say there is a 1/6 probability it moves from 1 to 0. There is a 1/3 probability it moves from 1 to 2. And we will add a loop that there is a half probability it stays in position 1. And for position 2, we have just looking at the example, just could be that I copied that wrong, in fact. We just take the example from the slides. So this one here, so I'm just putting it in a different color. In the slides, we have a half. And sorry again, it's actually just looked it wrong. It's a third. It's correct in the slide, so it's a third. And now for position 2, we have an edge from 2 to 1 where the probability is a 1/6. And we have the probability to go from 2 to 0, which is 5 divided by 6. So if you look into the probabilities, you may notice that certain probabilities have to add up to 1, and we will discuss this in a moment if there is any specific requirement for this to be a valid system. But we'll discuss that in a moment. We first want to see how we can actually represent this matrix or this graph as a matrix. So we can say we have a matrix M. We're just using the same approach as before. And I'm just putting these comments here so we're all on the same page what these rows and columns actually mean. We have incoming edges to node 0 from 1 and 2. From 1, the incoming probability, the one I'm highlighting now in blue, this is 1/6. And from 2, we have an incoming probability, which is 5 divided by 6. And there's no loop in 0, so we put a 0 here. Now, for node 1, we have a loop, which is this a half, and we put that here. 1 has an incoming probability from 0, which is 1/3, and this one here, and an incoming one from 2, which is a 1/6. And I want you to send me the entries of the last row um, of this matrix, which would correspond to the graph. And you can just send me the two entries in the chat and we'll compare them. So let's start with the last entry. It's 0 since there's no loop in 2, and 2 has an incoming one from 0, which is 2/3. And then we have the 1/3 here. So with this matrix, we can represent this graph over here. So it's two equivalent representations. And what we can do again is, if we have now this probabilistic system, say we have some state x, we can say x is our initial state. Its first entry is 1/6, then 1/6 and 2/3. Very importantly, row vector transposed. This is our state, and we see it's a valid state because the entries add up to 1. And now, and remember what this means. It means there's a 2/3 probability that the marble is in position 2 and a 1/6 respectively for position 0 and 1. Now we can do such an evolution again that we have matrix M and our state X, which we multiply from the right. I'm just copying the matrix from before, which was 0, 1/6, and 5/6 as before. Then 1/3, a half, and a 1/6, 2/3, 1/3, and 0. And our state X is, which we just defined before, 1/6, 1/6, and 2/3. Now we can multiply the matrix with the vector from the right. I will start with the first entry. So we have this row here and our column. Now we got a 0 here, and we have this 1/6, 1/6 times 1/6, which is 1 divided by 36, plus we have our 5 divided by 6 and our 2/3, which is 4/6. So 5 times 4 is 20 divided by 36 plus this one from here. So it's 21 divided by 36. And it's your task now. You can also use a calculator if you wish to tell me the next two entries. So multiplying the column vector with this row and with this row, and tell me the numbers. I'll give you a moment for that. So anyone has a suggestion for the next entry? So one person asked, how did we define X? Well, as before, also with the deterministic system, we just have one arbitrary X that is a valid state. Like we initially defined, there's a certain number of marbles that we start with. So we start with some probability distribution in X here. And it's just something we randomly defined, but doesn't matter because all we need to do is to evolve the system into by one time click. So one person said the next entry is a fourth. Yes, concretely it's 9 divided by 36. So we just use the same denominator that we can easily add this up. And the last entry is a sixth, or 6 divided by 36. And we see that these entries here, they just add up to 1, which means that y is a valid state. If you didn't add them up, or if you add them up and it's not 1, then something went wrong. Either you did some wrong calculation, or our transition matrix has some problem. And it turns out there are constraints for this transition matrix so that we actually have a proper probabilistic system. And this is something I will show you now in the slides. So here are the calculations we just did together. And before in the slides, we only have this matrix representation and the graph that we developed together. And now, in order to deal with proper probabilistic systems, we now have a constraint, or two constraints. We say the sum of all the weights leaving a vertex is 1, and the sum of all the weights entering a vertex is 1. And that's something we saw here. So 0 has two incoming ones, this 5 divided by 6 and this 1 divided by 6. And it has two outgoings, 1 2/3 and 1/3. If you look at position 2, has two incoming ones, 1/6 and 1/3 and 2/3, which are the incoming ones, and the outgoing ones are 5, 6 and 1/6. And for the 1 here, it's a bit more complex. So it has outgoing ones, which are a 6th and a 3rd, but it has an outgoing one of a half, and that outgoing one is also an incoming one. So we have the other incoming ones, which are here a 3rd and 1/6. So we see all of this leads to this matrix here, which represents the dynamics. And this matrix is a so-called doubly stochastic matrix. You'll see the term very soon in the slides. In a doubly stochastic matrix, we require that the sum in each row and the sum in each column must be 1. So these entries add up to 1, these entries add up to 1, and these entries add up to 1. And it's the same for the columns, that in each column, the sum must be 1. And if you have that, then we have a so-called doubly stochastic matrix. And these are the matrices we need in order to have proper probabilistic systems. So it's an important term, a doubly stochastic matrix. Later, when we deal with quantum systems, we don't deal just with probabilities between 0 and 1, but rather we will deal with complex numbers. But there is also some way how we can convert these complex numbers for a check into real values. And then we will later see the term doubly stochastic matrix again. So important term that you need to remember. And for your matrices, always check that they are doubly stochastic. Now we will see something quite interesting. By convention, we had always multiplied our vectors from the right with the matrix, because we made a very important assumption or a couple of assumptions, because we always said also the way these matrices work is the first row represents the first node and the incoming values or the incoming weights, not the outgoing ones. And because we defined the matrix M that way, we always multiply from the right. I told you before, we can also multiply a vector from the left. With this one here, what would happen if you try to multiply the vector x as is from the left? Would this work or not? So let's say we just flip m and x, and I want to multiply x from the left as a column vector with this matrix. Does this work or not? Maybe tell us in the chat if you think we could just flip this. And we got a few answers which are all correct. That would obviously not work because the dimensions are wrong, and that would not be a valid operation. But it turns out we can do something with x. And what we have here is, so far we've always worked with column vectors. And now let's say we have a new state w, and that's a row vector. So we don't work with a column vector, but now with a row vector. And we can multiply this row vector w from the left with matrix M. Because that's fine, because I have 3 entries here, and then in a column I have 3 entries as well. And if I multiply this together, I will get a new row vector. Since you've all done linear algebra, this would be fairly easy for you to test out. And so we have a row vector multiplied with this matrix from the left, and we get a new row vector. Now, why do we suddenly use a row vector and not a column vector anymore? You will later see this in detail when we study quantum systems. If I multiply a row vector from, or let's revise, before I used a column vector and multiplied it from the right. And we said this was one time click into the future. How the state evolves into a new state by doing one time click of the transitions. Now, do you have any clue what could happen if I multiply from the left? What could be happening in terms of the dynamics? Do you have a suggestion? And if so, maybe send it to the chat. What happens if I multiply a row vector from the left? What kind of dynamics could that represent? And we got a suggestion if it's one time click backwards. Yes. So as I multiply a column vector from the right to move one time click into the future, I can multiply a row vector from the left to move one time click into the past. So if this is my state, a third, 0, and 2/3, I move back in time, then I have this state. And if I use this state as a column vector and I multiply it from the right, I will get this state here. Because this is the past state, and if I take it as a column vector multiplied, I go into the future, or I take this future one as a row vector multiplied from the left and I go back in time. This is a very important principle that we will need in quantum computing all the time, because in quantum computing we will do something that we call reversible computing. That in quantum computing it's required that we're able to undo all of our operations. It's something you cannot do in a traditional digital computer. But with a quantum computer, it's possible. And this is a very important principle that we will later see again when we don't put in real values in here, but actually complex values. What we can also do is, if we take our matrix M, which was before, so this one here, this dynamics, I can also transpose M if I wish. Transposing is a simple operation you have seen before. And if I transpose, I'm actually just reversing these edges. And what happens is, if I transpose M, I would also have the dynamics to go back in time. So I could have M transposed and multiply a state from the right as a column. And what I get is actually going one click in time back, not forward. Do you all understand this? This is a very important principle for now. Maybe just confirm with a positive or negative reaction if you got that concept. And maybe a few more reactions, please. So, looks good. Then, um, there are a few more tricks or examples just of what we have seen before using the transpose and using this column or this row vector, which was W, and transposing it. Then we get a column vector. And these are just the same numbers as before, but this time working with the transpose. And finally, this leads to something that I have formalized here, which is this time symmetry, because maybe you remember this from linear algebra. It's something we didn't revise, but if you have M transpose times W transpose, and it has nothing to do specifically with our matrices here, but say more generically from linear algebra, um, you may remember this rule that if you have M transpose times W transpose, it would be the same as multiplying W with M in just the opposite order and then transposing that. That would be the same. Anyone remembers this rule? It's something you would see in your first or second semester when you study linear algebra. Anyone remembers this rule here? Okay. So one person, so probably most not. I remember I saw this in my first semester when I studied linear algebra, and actually this with this one we can show that there's a time symmetry, and the consequence is if we multiply on the right of M, this takes the state from time t to t plus 1, and multiplying on the left of M takes the states from t to t minus 1. And this time symmetry is something super important we will need all the time then in quantum mechanics and quantum computation, but we will use this then and work with complex numbers. Here we've just motivated it with our probabilistic systems. And as for deterministic systems, we can multiply M with itself to move by 2 time clicks into the future. We can also have M to the power of K, which means we go K time clicks into the future. And obviously you can also multiply from the left a row vector with M squared. That would mean you go 2 time clicks into the past, or K time clicks into the past if you have this matrix M to the power of K and you multiply a row vector from the left. And again, this is something you're most welcome to test at home. We have our matrix M from before for our probabilistic system, and we multiply it with itself. We would get this matrix here. And if you check this at home and you get this matrix, you will also see that it's a doubly stochastic matrix, which is always required, because if the matrix was not doubly stochastic, we wouldn't be dealing with a proper probabilistic system. Remember, doubly stochastic means each row must add up to 1 and every column must add up to 1. Now, we will look into a few other examples from a probabilistic perspective. So we just look at a few more systems and we will make some interesting observations. We will look now at a so-called probabilistic. So we will look at a couple of probabilistic experiments, like a probabilistic billiard game. We will look at a probabilistic double slit experiment. And later we will turn them into quantum experiments, and then we will see that they behave a little bit differently. But we start with them from a probabilistic perspective, simply to get a little bit more practice of what we have done so far. So we will have now the stochastic billiard game. And we will have the following system. So we have 4 vertices and 4. And what we see is when we look at these transitions, we will have transitions from 0 to 1 and 0 to 4, which is each time a half. We will have from 1 to 0 and from 1 to 3, which is also a half. We will have from 3 to 4. Oops, and I'm just correcting this. It's not 4 actually, just the names, we put the names correctly. So this was 0, 1, and then this is 2 and 3. So we have 4 entries. And these transitions here, so from 2 to 3 is also a half. From 3 to 2, it's a half. From 2 to 1, it's a half. And then from 3 to 0, it's a half. We will only just rename these, so we just use exactly the same figures in the slides, so we don't mix that up in case you want to revise with the slides. And I just noticed, yeah, I noticed so Zoom, sometimes the screen share breaks. I also don't know what the cause of that is. And I've noticed it too. So the Zoom sometimes causes some problem with the screen share, but if I switch tools, I will run into new problems. And aside from the screen share issues that sometimes appear with Zoom on the iPad, everything else works. And that's why I'm not very keen to try a different system, which will probably cause lots of new problems. So when we use exactly the notation for now that this is 0, this is 1, this is 2, and this is 3. So we use exactly the ones as we do in the slides. And we can try to represent this now also as a matrix. Which we call A, and it's a 4 times 4 matrix. And I'm again putting here just these commons, which always help us to see what each row and column stands for. So 0 has incoming ones from 1 and 2. Concretely, we have this incoming here from 1 and this from 2. So we put a half there. There's nothing coming in from 3, and there's no loop. So these are then 0. We will have for position 1, which is this one up here, we have incoming ones from 0 and from 3, which is this one here. So a half here, 0, 0, and a half. And I want you to look at this graph and send me the entries of the next 2 rows. Maybe start with row 2, just moving the 2 a little bit further down and we got more space. So tell me what's the next row, what the entries would be. So the next entry for 2, which is this one here, 2 has incoming ones from 0 and from 3, which is again a half and a half, and then the others are 0. And position 3 has incoming ones from 2 and from 1. So we put that here and here and have our zeros there. So the answers we got in the chat, they looked fine for the 3rd row, and I just put here the 4th row. Now we can test out some stuff, and we can start with the following start state, which we can call X. And in X, we say that the marble is at position 0. So we have a 1 and then all zeros. And now we will try to evolve this system. So we take our state X and multiply it from the right with A. And I will not copy and paste the whole matrix A again and X, but rather I want to know from you, what do I get when I multiply X from the right with A? We can write this as a row vector just to keep space. You can quickly look at that. It's fairly easy. So X is a column vector. We just write it down as a row vector and you multiply X from the right with A. So what values would you get that, for example, we call Y then? We got the right answer. So we got 0, a half, and 0, because we only have this 1 in here and all the other entries are 0. So only these 2 halves, we would get anything positive, and since all the other entries are 0, these ones here would anyway get ignored. So this is why, so A times X is Y, which is 0, a half, and 0. And now we will multiply Y with A. And this one may look a bit more complex than it actually is. So I would quickly copy the matrix. We're all just on the same page because we will make an interesting observation. And Y we just got before, so it's 0, half, and 0. And I want you to multiply now Y from the right with A and tell us what your result would be. And if you have a suggestion for these entries of the result, tell us. And what we got is a half, 0, 0, and a half, and that's correct. 0 doesn't look nice. Just write it again. Fairly easy to calculate because we have these two entries here and they only match here, and then it's a fourth plus a fourth, which is 2/4 or a half for the first and the last entry, and otherwise we just match with the zeros. So what we see is here, when we look at our system, so we've started with the entry. We said the marble was in position 0 when we started with X. Then it went with equal probabilities to 1 and 2. And then we evolved more by one-time click, and then it's with equal probabilities in 0 and 3. And if you keep doing this, you will just notice that the marbles, they act like a billiard ball, and they continue to just bounce back and forth between our nodes 1, 2, and 0, 3. Just a simple system and dynamics, and you're probably wondering, why did we look at that? We will later in this chapter or in today's lecture see that there is a quantum version of this example. And the quantum version will behave differently. So once we don't use real numbers but complex numbers as probabilities, we will see that this behaves in some totally different way. Then we will do one more example from probabilistic systems. Just switching back to my slide deck. So this is what we just looked at, the stochastic billiard game. I'm not providing the in detail calculations here, but we've just done this on the whiteboard, and we will see a quantum version of this example very soon. Now, what we will see today and next week when we look at quantum mechanics, we will see the double slit experiment. Who of you remembers or has seen the double slit experiment before in some physics class? Either in your undergrad or maybe in high school, if you did your A levels in quantum, or if you did your A levels in physics, you may have seen this. And maybe also send me some more negative responses, because I largely see only positive ones and not that many negative ones, but I guess there are more who have not seen this. So the double slit experiment is a very interesting quantum experiment. We will see it later and next week, but we will start with a so-called probabilistic double slit experiment. And this probabilistic double slit experiment is just simplified. And what we will see is that there are two slits in a wall. And there's a shooter, and a good shooter would always get the bullets through one of these two slits. And there's a 50% chance that the bullet will travel through the top slit, and a 50% chance it will travel through the bottom slit. And then there are three targets. So once your bullet is through a slit, there are three targets on the right of each slit that the bullet can hit with equal probability. And you can visualize this as this one. So we have a gun and we shoot bullets. They either go through this slit or this slit, and then from each slit, the bullet, say if the bullet goes through the top slit, at the next stage, the bullet would go into one of these three targets, or if the bullet goes through the bottom slit, it would go into one of these three targets. This is a simplification of the real or the quantum double slit experiment, but we will start with a probabilistic double slit experiment just to evolve step by step, and for those who have not seen it before, that you become more comfortable. There is a graph to represent this, and because this graph is quite important, and we will see all of this again when we look at quantum mechanics. I will quickly copy paste this for you and explain it step by step. So we do the probabilistic double slit experiment. And what we have is we are starting and we shoot the bullet. So when the experiment starts, we are just move this a bit further down that we get enough space. We are in position 0, and then we have positions 1 and 2. And we said the bullet would go through through the top slit or the bottom slit with equal probabilities. So this is a half and this is a half. And then this was one time click. And then in the next time click, the bullets would go into one of these three targets. So we got target 3, target 4, target 5 for the top slit. And since this would also all go with equal probabilities, it's 1/3, 1/3, and 1/3. And for the lower slit, we also saw that there is this target in the middle from before, because it's 5 targets. So from the lower slit, we could go into target or into the third target, which is here position 5. Plus we have the remaining targets to which we could go from the lower slit. So it's 1/3, 1/3, and 1/3. Now we can do 2 time clicks, but we somehow need to build the matrix later in a way, ideally a doubly stochastic matrix. We will later see if it's actually a doubly stochastic matrix or not, but we should still build this mechanism so that we can actually have more time clicks, but the system won't be evolving anymore, but we still better define it. So we put in positions 3, 4, 5, 6, and 7 a loop. So it's all with probabilities 1, so that we just, if we have more time clicks, obviously the bullet cannot move further. It's in one of these targets. Now, it turns out we can take this matrix or this graph, and we can also define its corresponding dynamics or its matrix in a or its dynamics in a matrix. So we can call this B, and this will be a matrix of size 8 times 8, because we have 8 positions, 0 to 7. And we can quickly think about what this matrix would look like. And we get quite big. So let's start. What do you think the first row of this matrix would look like? It's a fairly simple row. Remember that position 0 or vertex 0 has no incoming edges. So what would the first row look like in our matrix B? It's all zeros. So it's 8 zeros. Just writing this down. 0, 0, 0, 0, 0, 0, 0, 0. I can still put the comments here: 0, 1, 2, 3, 4, 5, 6, 7. Now, what would the next 2 rows look like? The next 2 rows look the same. And I'll just see any of you has a suggestion what the next two rows would look like, which is for vertices 1 and 2. So this is our graph. And we see that, I'll just wait and see if anyone will send something to the chat. We have these two incoming edges. So we have a half and a half. And then all the other entries are 0 as well, because vertices 1 and 2 only have an incoming edge. Each of them has an incoming edge from 0. So we put remaining. Oops. There's a comment in the chat. We will discuss this later. I've seen it and it's anywhere on my agenda to discuss it. But we first build the matrix together step by step. And now we can think about what the next few entries would look like. What we see is there are these loops in positions 3, 4, 5, 6, and 7. These loops would lead to ones in the diagonal, because from 3 we have a loop to itself from 4, 5, 6, and 7. And 3 has an incoming edge from 1, which is this one here. 4 has an incoming one from 1, and 5 has an incoming one from 1. So we can put these, and I put them in blue. So we have a third here, a third there, and a third there, which are these incoming ones from 1. Plus we have the incoming ones for 5, 6, and 7 from 2. So we have this 1/3 here, 1/3 there, and 1/3 there. And all the other entries are 0, so we can just put them all to 0. And I hope I don't miss any zeros, but it's anyway all well typed in the slides. So this is a matrix. Hopefully all the zeros are put in there. And we observe a few things. For example, we see this one here. We have these two 1/3 in 5 coming from 1 and 2, which are just these two ones. What do you notice about this matrix? Is anything in a matrix as you would expect, or is something wrong about the matrix? One student already had some question about that in the chat, but I first want to collect the opinions from the others. What do you notice about this transition matrix? The columns, someone writes, the columns would add up to, each column would add up to 1. Yeah. What happens to the rows? The rows do not add up to 1. And this is one of the questions we got early from a student. He asked if the sum of the weights is not 1. So we see this matrix is not doubly stochastic. Um, so it's actually not a proper probabilistic system that we are dealing with, but that's also not our goal with this experiment. But rather we will use this system here for our probabilistic double slit experiment to get a few initial ideas, even though it's not a proper matrix that we would be used to, but we only do time clicks into the future, not into the past with what we try now. And it just gives us some initial ideas, and that's okay for now. So we have described this matrix B, and we will look at it in the slides. So this is our probabilistic double slit experiment. This is the matrix B that we have just developed together. And what we could start with is we say our bullet is in state 0. So our start state would be a 1 in the first entry and then 0 in all the other entries. We would multiply it with B, so multiply the column vector from the right. And what we would have is 50% here, 50% there. And then we would have that intermediate state where we are 50% in one, 50% in two with our bullet. And we would multiply that new state again from the right with B. And then we would get some distribution where we are in states 3 to 7. However, do you remember what we can do? What can we do if we want to do 2 time clicks directly with a computation? What do I need rather than using B? Which matrix do I need? We've looked at this before now a few times, also with deterministic systems. Can you tell me in the chat or turn on your mic? What could I do to make this transition directly? We got the right answer, B squared. So we multiply B with itself, which is something you are most welcome to try out at home or not. It's up to you. But I've put it here in the slides already, and I'm not copying this to the whiteboard, but B squared is a matrix like this. So B squared would allow us that we have our start state, and we multiply it with B squared, and we do 2 time clicks into the future. So we finish the experiment, we shoot through the double slits, and then to the concrete targets. And we take our start state where the bullet is in position 0, which is just a 1, and then all the other zeros. And remember, it's a column vector, so we put it here as a row vector that we transpose. And then if we multiply x from the right with b squared, we would get something like this. 3 zeros, and then 1/6, 1/6, a third, and then 2 more times 1/6. This has to do with the following. Because if I do two time clicks, the bullet is not here anymore. The bullet has evolved and would be now in positions 3 to 7 with a certain probability. And it's 1/6 for 6 and 7, 1/6 for 3 and 4, and 2 times 1/6 for position 5. Because there are 2 ways how we can shoot into target in 5, either through the top slit or the bottom slit. So the probability that the bullet ends in 5 is greater than in the others. So that's why this 1/3 here refers to position 5, which is this middle target, which we can reach through both the top and the bottom slit. Are you all still with me? Does that result make sense to you? Maybe confirm with some reaction. I have also written the result here, and what I've said orally is that that position in b squared 5, 0, we have a 1/3 here. Feel free to try this out at home also if you wish. It's just a more formal explanation, but we've just clicked through this and looked at the graph, and we saw why we have that double probability than in the other targets, because there are two ways we can reach this target. Now, all of this here adds up to 1, so this is a valid state. So even though we didn't have a doubly stochastic matrix, the outcome is correct. And we don't need a doubly stochastic matrix here because we're not interested in going back in time in this experiment. And it's anyway just a simplification of the real quantum double slit experiment. We will explore the actual quantum version of the double slit experiment later in the next section of this chapter. And then we will see that something very strange will happen, that these probabilities don't add up, but they actually start canceling each other out. And for that, we need complex numbers. We will now look into quantum systems. We have started with deterministic ones, then probabilistic systems, and now we want to model quantum systems. And like this, we get step by step closer to the goal of the course, quantum computing. Now, I noticed the screen share failed again. It will be back. So I'm sorry if there are sometimes screen share issues with Zoom. I'm bothered about that too, but with new tools, new problems come. And other than that, the Zoom works quite well. So we will model quantum systems now, and we don't use probabilities any longer as real values between 0 to 1, but rather we use complex numbers. So now complex numbers, and we will specifically deal with complex numbers like C, where the modulus squared of C is a real number between 0 and 1. So the modulus squared of the complex numbers we'll be dealing with is a real number between 0 and 1. Why are complex numbers needed for what we want to do now? Why are traditional probabilities not enough? Well, when we have classic probabilities, which are real numbers between 0 to 1, we can always add them up. But with complex numbers, they can cancel each other out. And it's something we are unable to do with probabilities. So complex numbers can cancel each other out. And I'll show you an example for that. We use now complex numbers that for which the modulus squared is not in this range, but it's just one example. What we mean by canceling out. Imagine I have C1, which is 5 plus 3i, and I have C2, which is minus 3 minus 2i. Now, also that you can actually revise what we did last week, I want to know from you what's the modulus of C1. Please take a look into that and send your response to the chat when you know what the modulus of the C1 is. It's the square root of 34. Well, we just do 5 squared plus 3 squared. So it's a square root of 25. But we don't really care now about the modulus, but the modulus squared is something we keep using a lot now, and you will later see why the modulus squared, because this has to do with quantum mechanics. So the modulus squared of C1 is 34, because we just take the square root result and square it, so the square root is just disappearing. And what is the modulus squared of C2? I want to know this from you. If you know the answer, send it to the chat. It's 13 because it's just 9 plus 4. And now we see what canceling out means. Imagine I have C1 plus C2. Adding up these two complex numbers, I will get 2 plus I. Now I want the modulus squared of this addition. So the modulus squared of C1 plus C2 is the modulus squared of 2 plus I. It's 5. And 5 is less than the 34 here, and 5 is less than the 13. So we've added two complex numbers, but they start to cancel each other out. And that's something we're unable to do with real numbers or with probabilities that are real numbers between 0 and 1. And there's more about this, which we will see in the quantum mechanics chapter next week. But for now, just bear with me that complex numbers are important to model quantum systems. And we'll see more details as we progress in this course. And the fact that complex numbers can cancel each other out when we add them, so there's a well-defined physical meaning in quantum mechanics for this, and this is called interference. Interference. So not inference, very important, interference. And this is a fundamental concept in quantum mechanics, so that probabilities can cancel each other out. Actually, the concept of interference also exists in classical wave mechanics, so waves can cancel each other out. So it's nothing just constrained to quantum mechanics when it comes to this term. You remember we before discussed valid probabilistic states, and a valid probabilistic state, we said the entries need to add up to 1. Now, when we come to quantum states, let's look at them. I have one example here. So say my example is the following state. I say X. So write it down as a row vector that has 3 entries. So 1 divided by the square root of 3. The next entry is 2i divided by square root of 15. And the last entry is the square root of 2 divided by 5. This could be a sample quantum state. What we see here is the first entry only has a real component. Here we only have the imaginary component, again a real component, but all of them are complex numbers. And as we required before for probabilistic states that the sum of the entries must be 1, here we require the sum of the modulus squared of the entry must be 1. So sum of the modulus squared of the entries is 1. Now I want to know from you, is this a valid quantum state? You can think about, you can first of all calculate the 3 modulus squared. So we can break this up step by step. So we have this first entry, 1 divided by the square root of 3. I want its modulus squared. So maybe you can write out these 3 results here step by step in the chat. So we have the first intermediary result. Then we have 2i divided by the square root of 15. I want to know what's this modulus squared and the modulus squared of the square root of 2 divided by 5. Always assuming these are all complex numbers, even if they have only a real part. So what's the first modulus squared? We have a suggestion that this is 1/3. Then the next one is 4 divided by 15. And the last one is 2 divided by 5. Now, does all of this sum up to 1? What do you think? Yes or no? Yes, that's correct. So these 3 entries, they add up to 1. So state X is a valid quantum state because we said the sum of the modulus squared of the entries is 1. So well done. Now we can look into the dynamics of quantum systems. So we've now seen a quantum state, a bit more complex than our probabilistic states. Now we look at the dynamics. We can again look at one example system. For now, it has 3 positions. We have 0, 1, and 2. And we're just, this time we are using complex numbers. So we say there's a loop in 0, which is 1 divided by the square root of 2. Then we have a loop in 1, which is I divided by the square root of 2. So this is just an example from the book. And we have a loop in position 2, and we say this is I. So you see now in the transitions, we can also put complex numbers. And we can do more transitions, say between 0 and 1, and 1 and 0. So from 0 to 1, this is minus I divided by the square root of 2. And from 1 to 0, it's 1 divided by the square root of 2. So we just plug in complex numbers rather than real numbers. And we can also describe this as a matrix, which is matrix U. And we see, we again put the commons there, 0, 1, and 2, 0, 1, and 2. And we see that the first entry is the loop in 0, which is 1 divided by the square root of 2. Then 0 has an incoming edge from 1, which is also 1 divided by the square root of 2, and none from 2. You can send me the next row of my transition matrix. So just look at the graph and see how you would convert this into our matrix scheme and share it, maybe the first row with us in the chat once you have done it. It's fairly easy now. We've practiced this a few times with with regular probabilities. We just apply the same scheme to complex numbers. So the first entry is the edge from 0 to 1, which is minus I divided by the square root of 2. Then the loop, which is I divided by the square root of 2, and the 0 in the last row is just the loop in position 2, which is I. I will quickly switch back to my slides. Everything I have shown you is also in the slides with some more text and the example that probabilities cancel each other out, or the complex probabilities. We've defined the term interference, and we saw what a valid quantum state is. And then, yeah, we're doing the dynamics, and this time we put in complex numbers. We've seen this one and its corresponding matrix. We don't require that this is doubly stochastic matrices. We will later see in a few minutes what kind of matrices we use here. And obviously, we can also do transitions into the future. Say we have some state X, like the one from before, which is a valid quantum state, and we have our transitions and we do one time click into the future. And we have finally this one here. Feel free to do this at home or step by step, but eventually this time we're just, this would take a little bit longer that they look that way, but because you have real and imaginary parts. But eventually you would get this state here, and it's still a valid quantum state, which we call Y. So it's just the same stuff actually as before, but we just plug in complex numbers. Now, there is a relation to doubly stochastic matrices. And very importantly, the matrices we use here to have proper quantum systems. So for probabilistic systems, we require doubly stochastic matrices. Now for quantum systems, we require unitary matrices. Who of you remembers unitary matrices from last week? Maybe send me a green reaction or thumbs up if this is something you remember, or thumbs down if this is something you forgot. Fine, everyone remembers. So a unitary matrix, I'll quickly go back. So from what we did last week, just need to find the corresponding slides because we also have some people watching. Last week, we introduced the concept of an adjoint matrix, A dagger. So we take A and we use the conjugate on each complex number in there, and we also do the transpose. This is the A dagger, the adjoint, and the unitary matrix. We have a matrix U, and U dagger times U as well as U times U dagger must be the identity matrix. And if this holds true for U, then we have a unitary matrix. And I told you this would be super important. And finally, it's time to use unitary matrices. And we will study that now in a little bit greater detail. So we use unitary matrices to describe our dynamics in the quantum system. And so we require that. And it turns out that if we take our our matrix U, so our unitary matrix for quantum systems, and we calculate the modulus squared of every entry. So this one here means taking each entry and calculating the modulus squared of each entry. So it's not squaring the matrix, but we take index ij in our unitary matrix and calculate the modulus squared, and we do this for every entry. Then we will eventually get a doubly stochastic matrix. So the modulus squared of all the complex entries in our matrix U forms a doubly stochastic matrix. So this was our unitary matrix from just before. Remember this one here. And if you calculate the modulus squared in there for each entry, you would get this matrix here. And this one is doubly stochastic. So this is the relation to the doubly stochastic matrices from before, that we calculate the modulus squared of all the complex entries in U, which must be then a doubly stochastic matrix. Now, something very interesting will happen, and that's why we actually use the unitary matrices. Remember, we have some state V, and if we multiply V with U from the right, we have some new state, whatever we name it, but we just do one time click into the future. Now, how can I undo operations? How can I go back in time? When we studied probabilistic systems, we saw we could multiply from the left as a row vector and we could undo something. But we also saw if we take from the probabilistic systems the transition matrix and we transpose it, then I could also multiply a column vector from the right to go back in time. And that was this time symmetry concept we introduced just 1.5 hours ago. Now, with the unitary matrices, we can do something quite similar. So I have evolved by taking my state V and multiply it with U. And I could undo this by multiplying from the left U dagger. So the adjoint of this unitary matrix, which we just saw, we have the the conjugate of each entry in the adjoint and the transpose. And the transpose is something we saw before, which we could use to go back in time. Now here, this is strongly related to the transpose, but we have complex entries, not real entries. So we need a conjugate of each entry. And if we multiply this from the left, and you remember, if I have U dagger times U, this just undoes each other. This just leads to the identity matrix. And if we say this is now for 3 times 3 matrices, U dagger times U leads to the identity matrix. So what we can do is we can go back in time using the adjoint, so the U dagger. While we used before the transpose for probabilistic systems, here for quantum systems, we use the adjoint. Is this something you understood? Maybe just signal with a yes or no. And this is why last week we spent some time on introducing unitary matrices, because I also told you that as a quick preview last week, it helps us to undo operations. And when we look more into quantum computing in 2 weeks or so, we will see why this unitary matrix is so important, because they allow us to undo operations. And this is something crucial we need to do in a quantum computer when we have multiple operations and apply them. And it's something we will again see next week when we look a bit more into quantum mechanics. So we will come back to this evolution here quite a few times. So with the adjoint, we can go back in time, and eventually these two, this product, it just undoes this, and that's the identity matrix which is neutral here, so it's just V. But the order is very important. We always multiply the matrices from the left in exactly that order. We will also see in 1 or 2 weeks what happens if we have multiple operations or different evolutions of a system, because how you could imagine you could be in a quantum computing context, maybe some fundamental operation, some quantum gate that does something, and I may have multiple quantum gates, not just one type, but different ones. And then I also want to be able to undo some of them, so I need to put these U's and these adjoints in the right order. So if I have more than one system that I could use there. But that's something we'll see when time comes. We step by step evolve. So we've seen the time symmetry before for probabilistic systems, and now we see this for quantum systems, where we use eventually the unitary matrices we spent quite some time on last week. If you have a matrix like I3, so just the identity matrix, we could also visualize this here, because eventually this would just lead to 3 loops in position 0, 1, and 2, no other transitions. So this would be actually a visualization of I3 in case you wish. Before we had our U, we can also calculate its adjoint, so the U dagger. And if you wish, you could also try to visualize this. But last week you learned how to calculate adjoints. We've seen U before. So in case you want to revise and get extra practice by calculating the adjoint, please do so. And eventually this would be U dagger, and you could also visualize it here in case you wish. But that's just some extra practice for you. Now, before we looked at the probabilistic billiard game, and we will now look at the quantum billiard game. And for this, I will return to my iPad. And so before we studied the probabilistic billiard game, and so we could also study a quantum billiard game. Remember that with the probabilistic the probabilistic billiard game, we've seen this here before. We started in position 0, and then we were half-half in 1 and 2, and then in further time clicks in 0, 3, and then this kept alternating between 0, 3, and the next state between then 1, 2. Now, the quantum billiard game will be a bit different, as we will see now. So we have the quantum billiard game. And for this, we can again provide our graph. It's just as before, but we will use complex numbers, and then something quite different will happen. So we put in our transitions here again, and they are as before in terms of the structure, but we put in complex numbers. And from 0 to 1, it's 1 divided by the square root of 2. From 0 to 2, it's also 1 divided by the square root of 2. Then, and I saw the screen share failed again, I'm sorry. I don't know, usually Zoom doesn't cause that many problems, and I did an update of Zoom before. Maybe it's the iPad that needs to be replaced. I also don't know that, but just keep progressing. Then the transition from 1 to 3 is minus 1 divided by the square root of 2. from 1 to 0, it's 1 divided by the square root of 2. Then from 2 to 0, it's 1 divided by square root of 2. From 2 to 3, it's 1. So from 2 to 3, it's 1 divided by the square root of 2. And then from 3 to 1, it's minus 1 divided by the square root of 2. And from 3 to 2, it's 1 divided by the square root of 2. We can also write this out as a matrix, and we can say this is matrix A. It's again a 4 times 4 matrix. And we can just think about what does the matrix looks like. What does the matrix look like? So 0 has incoming ones from 1 and 2. So I have zeros here. So, and this is 1 divided by the square root of 2 and 1 divided by the square root of 2. 1 has incoming ones from 0 and 3. From 0, it's 1 divided by the square root of 2. Then no incoming ones from 1 or 2, but from 3, which is the minus 1 divided by the square root of 2. Remember, these are all complex numbers, even though they just have a real part. Then the 2, the next row, has almost the same. It looks almost the same because it has an incoming one from 0, which is positive. Nothing from 1 and 2, but from 3, which is also positive, 1 divided by the square root of 2. And then the last row has 3 has incoming ones from 1 and 2. From 1, it's minus 1 divided by the square root of 2 and 1 divided by the square root of 2. Now, what you will see is if you take a start state x, which is again 1, 0, 0, 0, transpose, and you multiply a times x, what happens? What state do we get? You can just quickly try this out for yourself. We have our matrix up here. And I multiply state x from the right with a. Which state do I get? You can send it to the chat once you have an answer. We got the first answer already. So the first entry and the last entry are 0, which makes sense because this 1 here only matches with this one and this one. And that means the entry is then, or the next two entries in between, are 1 divided by the square root of 2 and 1 divided by the square root of 2. All the other entries, so the first and the last one, are 0. But what gets interesting now, and this is called y, if you multiply y with a, you will see something super interesting. We can try this out together. So we have y, and the first entry is 0. And the last one as well. That means if I multiply this with the second or third row, this will just lead to zeros because I have these zeros here and I have these zeros there. So eventually this will all be 0 for the second and the third entry, so 0, 0. The first row is interesting because we have this 0 and we have 1 divided by the square root of 2 and 1 divided by the square root of 2. So we multiply these entries with each other. So 1 divided by the square root times itself is a half. Plus, we take this one and multiply it with this one is another half. So this leads to a 1. And what do I get if I multiply y with a with regards to the last row? What's the result if I multiply these entries and sum them up? So what would be the last value of a times y? And it's 0. That's correct. Because we have a positive entry here, but also a negative entry. And this will just cancel each other out. So we see this quantum billiard game behaves totally different than our probabilistic billiard game, because in the probabilistic one, we later had this alternation. But here we actually get back to the original state after the second transition. Fairly interesting. So the quantum billiard game behaves totally different to the probabilistic one. And we'll visualize this also in slides. So this was what I had shown you. And this was our starting state. After one time click, we get this state. And the second time click, we are back in the original state. And that's something we weren't able to do with the probabilistic ones because we only add up probabilities. We cannot just do interference to cancel out probabilities. But here it works because of the complex numbers. So they cancel each other out. And something you would actually find out that is quite interesting, you can multiply a with itself. So a times a, something you can try at home if you wish. And this will lead to the identity matrix. So another opportunity for extra practice if you wish. So this is the quantum billiard game. And before, with our probabilistic experiments, we also did a probabilistic double slit experiment. And we will motivate today the quantum double slit experiment. We will see it again next week. And the quantum double slit experiment is more complex because this time we don't examine bullets, which are large objects, which follow the laws of classical physics. And sometimes you see quite some text here in the slides. This is also for your revision for some concepts. It's not meant that I read this out, but sometimes it's sort of a good revision for you. And this time we use very small objects that follow the laws of quantum physics, which a big bullet does not. And this time we don't have a gun, but rather a laser, and we shoot photons, which are elementary particles, and they are the ingredients of light. And this time we shoot photons through the two slits. So this time the experiment looks a little bit different. It's not bullets, but we have a laser with this light here, a light source. And this time we shoot light through the double slit. And we still have our targets back here. And we make some assumptions that a photon will pass through one of those two slits. And we simplify the experiment a bit, and each slit has a 50% chance of the photon passing through it. And then behind this slit, we have 3 measuring devices, or behind each of the slit, we have 3 measuring devices, these ones, and these ones, but here we have this shared one as before. And you remember before when we studied the probabilistic double slit experiment, do you remember what happened in this target here for the probabilistic ones? What happened to the probability of the bullet ending up in there? Maybe just tell us, you can turn on your mic or tell us in the chat. So not the quantum one, but the probabilistic one. So we got the right answer. Here we had an increased probability because there were two ways to get there, either through the top or the bottom slit. But this time we're doing this as a quantum experiment. And this will turn out to be quite different, and you will see something different. Now, there is this graph here of these probabilities. I have not come up with these probabilities, but the literature has. And we will now develop this step by step, come up with the matrix, and then do the quantum double slit experiment and see what actually happens to this probability, especially of this one that was of our interest. So we will have a relatively complex graph. So double slit. And we have our start position 0. And we have position 1 and position 2. And with equal probabilities, we are going there, and it's complex numbers. So it's not probabilities. So it's 1 divided by the square root of 2 and 1 divided by the square root of 2, because what matters is that the modulus squared would finally add up here to 1, because we want this doubly stochastic matrix, as we've seen before, if I convert the unitary one to a probabilistic one. And then I have, again, these different targets or measuring devices, which are 3, 4, and 5, and 6, and 7. And in there, we have our loops. And this is very importantly a simplification of the double slit experiment. And also the matrix we will see is a simplification because much more stuff can happen, but we're not interested too much in this from a physics perspective. Rather, we want to understand a little bit quantum systems and compare them to the probabilistic ones. And this is not a physics course, it's a computer science course. But it will help us to understand some of the differences a bit better. So we have these probabilities here, these transition probabilities, which is -1 plus I divided by the square root of 6, then -1 minus I divided by the square root of 6, and 1 minus I divided by the square root of 6. Then we have 3 more here. This one here is -1 plus I divided by the square root of 6. Then -1 minus I divided by the square root of 6. And 1 minus I divided by the square root of 6. And you all know that we can also turn this into a probability or into a matrix, which we will do now. So P is our matrix, and I will just write out the matrix step by step. And then we will observe something quite interesting happening in this matrix. And we also put the comments up here. 0, 1, 2, 3, 4, 5, 6, and 7. So, what we saw, it's actually quite related to the probabilistic one. Node 0 has no incoming edges, so all of these values up here are 0. Node 1 and node 2, they have an incoming edge from 0, which is 1 divided by the square root of 2. This time it's simply complex numbers. Before it was real probabilities. Then what we see is the nodes 3 to 7 have no incoming ones from 0, but they only have something incoming from 1 and 2, plus we have these loops in 3, 4, 5, 6, 7. So we can already put in these loops. Then the other entries are 0. So these are just the loops as before. And then we have these remaining probabilities. So we have these 3 here in the next in the column, which I just write down again. So this is minus 1 plus I divided by the square root of 6. Then minus 1 minus I divided by the square root of 6. And 1 minus I divided by the square root of 6. And then we have these zeros. So these are just the ones I put in. So minus 1 plus I, minus 1 minus I, and 1 minus I. They are here. These entries are also 0. And then we have the next 3 entries, which is minus 1 plus I, minus 1 minus I, and 1 minus I, always divided by the square root of 6. So we just write them down here. Minus 1 plus I divided by the square root of 6. Minus 1 minus I divided by the square root of 6. And the last entry is 1 minus I divided by the square root of 6. What is interesting is this part here, and this will also have a lot of impact on the outcome of our double slit experiment, that node 5 has 2 incoming edges, one from 1 and one from 2. Just exactly this part here. So 1 minus I divided by the square root of 6 and minus 1 plus I divided by the square root of 6. And this will finally lead to something quite interesting. What do you notice about matrix P? We've said always our matrices must be unitary. Is this a unitary matrix? If you think it's unitary or not, answer in the chat. If you have a guess. So one person believes it's unitary. Any other guesses? Maybe let's do a vote. Green sticker means it's unitary. Red sticker means it's not unitary. And maybe a few more votes would be great. So there's a majority for unitary. It turns out the matrix is not unitary. And you could maybe see this already from quite a few zeros that are in there. So this matrix is not unitary. And there's a reason for that, because there are more possible transitions in the real double slit experiment because there are more possible ways the photon can travel in a real life physical situation. The photon could also travel from right to left. That's something we have not considered here. But this graph and the matrix would become too complex for that in order to see all the transitions. And that's something we also don't care about because we're just very interested in one effect that we will see now, which is the interference. And that's why it's not a proper unitary matrix, but for this experiment, it doesn't matter. We've seen this before that when we looked at a probabilistic double slit experiment, we failed to have a doubly stochastic matrix, as you may remember. And we have developed P now. I'll switch to the slides for now. So there are a few more matrices and I can just show you the relevant stuff. So this was our matrix P. We have developed step by step, and it's not unitary. And I've also explained here in the slides why it's not. We could calculate the modulus squared of each entry in P. And what you will see is if you calculate the modulus squared of every entry in P, it's just the same matrix we had in our stochastic double slit experiment or probabilistic double slit experiment. We've seen exactly this matrix before, which was also not doubly stochastic. And what we can do is now we can multiply P with itself, P squared, and you will see something super interesting in the P squared. So feel free to do this at home, or you just trust me that I've done the P squared correctly. And what we are actually most interested in are these two elements. Because before, when we had the probabilistic double slit experiment and we multiplied the matrix with itself, then we had two positive values here, and the outcome was later when we had our matrix or our start state and multiplied it with P squared. Then we can just go back, I think, to this. Just wait a second. So we actually are on the same page. So the probabilistic double slit experiment, we were interested in this part here. And then when we had our start state 1 and all 0, and I multiplied this with b squared, this here actually led to the 1/3 I had over here. But now, if I build my p squared, so from the quantum double slit experiment, I have my p and my p squared, I will suddenly have a 0 in here. And you can try this out. You can calculate p squared on your own. You will finally see something quite interesting. And I'm showing this also in here, what will happen. So if we have our start state, which is x, 1 and all 0, and I multiply it with p squared, the probability that the photon ends in our particular interesting position 5, that probability is suddenly 0. And not positive or greater than the other ones, but 0. Because these two probabilities, they cancel each other out. Next week, when we look more into quantum mechanics, we will look into the double slit experiment again, and we will look at not just one photon, but multiple photons. And what would happen is that this area would be dark. You would have some light here with a distribution and some light there with some distribution. But here it would be dark because these photons just cancel each other out, and eventually you would have no light over here. Is this something you remember from physics? Like some of you said, you remember the double slit experiment from school or from a physics class. So do you remember the outcome here? If it's light, that this cancels each other out. And we've seen some positive responses. We'll see this a little bit next week. But what I wanted to show you here is simply that these probabilities cancel each other out. So the probability of the photon being here is 0. And you're most welcome to try this out with the start state, and you multiply it with p squared. And what you would also see when you have p squared and you take the modulus squared of each entry, we also have a 0 here, which gives us, again, further evidence for this. And when you calculate p squared, you would see that that one entry that is so interesting, so the one at index 50, that one is 0. I show here why this is the case. So try on your own as a homework to multiply p with itself, and you will see that finally all of this cancels out for that one entry. And next week we discuss the double slit experiment again from a more thorough quantum mechanical perspective. There is some more information about the double slit experiment in case you want to read this, or you will simply see this next week when we discuss it in greater detail. There is a little bit more insights on quantum mechanics that I already want to provide you with. We will see all of this in greater detail next week, but it's already a sort of a motivation. And it's a lot of text now, but it's also meant for you to have a revision. So in quantum mechanics, in which we are now through our quantum systems, we will have states, state X. And we have these complex numbers as entries. So C0 up to Cn minus 1. They are all complex numbers. And we said that finally their modulus squared needs to add up to 1. That's one constraint. And this constraint is something we will explore in greater detail next week. But when we had our probabilistic double slit experiment, or in general, when we dealt with probabilistic systems, we always said that that bullet, for example, is with a certain probability in some position. That's how we interpreted for probabilistic systems this state vector. But it is now, when we look in quantum mechanics, actually not correct to say that we actually in here have probabilities of where the photon could be with a certain probability. So we could, for example, say we have some entry ck and we calculate ck modulus squared, which gives us some probability. But that probability from a physics perspective does not mean that the photon is in that position. We could say this before for probabilistic systems, but for quantum systems, we cannot say that this is the probability that it is actually there. Rather, in quantum mechanics, we have a concept called superposition, so that the photon is actually not in a single position, but rather in many positions, potentially in all of these positions at the same time. So what does that probability modulus of ck or ck modulus squared mean? It does not mean that this is a probability where the photon is. Rather, when I do a so-called measurement, that's a concept we will also discuss in greater detail next week. When I do a measurement, I collapse a quantum state into a classical state, and then our probability ck, we have the probability of measuring the particle at that position, not that the particle is with a certain probability at that position. Do you understand? You don't need to understand this concept in detail yet, but just from the wording, do you understand there's a difference of a particle is with a probability in a certain position, or I measure the particle with a certain probability at a position once I do measurement? Do you understand from the wording that these are two different concepts? maybe just confirm yes, no, green, red, whatever. We will explore these concepts, and they are difficult. We will explore this in greater detail next week. But just from the wording, sometimes I may also be sloppy in the next few weeks and say, with probability, whatever, we are in there. Actually, it's not that we are in there with that probability, but rather we're being measured, or we rather measure with a certain probability then. Because before we measure, our particle is actually in all of these positions simultaneously. And that's the idea of a superposition. So it's a far more advanced concept than our probabilistic bullet that was somewhere with a probability. And the bullet can only be in one position effectively if it's probabilistic. But here, these are quantum mechanical effects, and the particle can be in all of these positions simultaneously. And the probability is about where we measure it eventually. But we'll discuss this in greater detail. I understand if this is not fully understood by everyone yet. And that's why quantum computing becomes so interesting, because the real power of quantum computing is the superposition, so that we can simultaneously process many states at a time, and this will lead to massive parallelism in a quantum computer, which we are unable to do with traditional computers. But quantum computers will come in a few weeks because we're evolving step by step with the theory. Now we're coming to the last subsection for today, for the last 20 minutes or something like that. And so far, we have always dealt with one quantum system. And imagine now, or we've always dealt with one system. First a deterministic one, then a probabilistic one, then a quantum one. And from a computational perspective, we could have a quantum system which is just one qubit, 0 and 1, and we have some transitions in there. But we want to deal in a quantum computer with multiple qubits typically. So we have multiple systems and we need to aggregate them into a composite system. So we assemble eventually larger systems, or we build composite systems. We will discuss this now, how we can combine several systems into one. We will work in these examples with probabilistic systems. And all the math we do for probabilistic systems works exactly the same for quantum systems, where we just use complex numbers. But in the first attempt, I want to keep this simple and rather use traditional probabilities, as you know, and you could just imagine if these were complex numbers, it would work exactly the same way. And in the coming weeks, we will need this anyway when we build our quantum gates in 2 weeks and stuff like this. But we start with, again, probabilistic systems now when we build composite systems. And we will develop this again on the whiteboard. Now we will study 2 very small systems and we build an aggregate system. So we have a matrix M. This time we're starting with the matrix. I noticed the screen share will be back very soon. Usually there are less issues with screen shares. Today there are particularly many. I'm very sorry about this because it also distracts me. So we have a matrix which is doubly stochastic, say 0, 1, 6, 5, 6, and 1/3, a half, and 1/6, 2/3, 1/3, and 0. And we can try to visualize this graph of M, which we have position 0, position 1, position 2. We can just put in these transitions. Well, we start. So 0 has incoming ones, which is 1, 6 from 1, and 5, 6 from 2. 1 has incoming ones from 0, which is 1/3. We have a loop of a half, which is this one, and this 1, 6 coming from 2 to 1. And then 2 has 2 incoming ones from 0, which is 2/3, and from 1, which is 1/3. You're all fine with this, right? Maybe thumbs up or thumbs down, but this is what we have done all the time today. Now we have another system, because first introduce our systems, and then we will try to build a composite system. So 1/3, 2/3, 2/3, and 1/3. And we can visualize the graph for n. And this time, just for the convention, so we've called this 0, 2, 1. And there's actually the circle here in black. This time we are using an A and B, so we are easier later able to distinguish between the one system and the other. So this position here will be called A, and this position will be called B. So you will later be able to see which comes from where. So the A, we have well, put a loop in red. We have a loop, which is a third here. And in B, we have a loop also with 1/3. And then these transitions are just 2/3 in each case. So very simple system. Now we want a composite system. And these composite systems, we will soon see how we can build it, but we assume now we have a state of the composite system. So I'm asking you to guess. We have the first system, which has 3 positions, and the second system has 2 positions. And now, if I build a composite system, so a joint system of these 2 systems, what do you think how many positions this would have, this composite system? If you can guess a number, what you think how many positions we would have? Because we have 3 and 2, and somehow we need to aggregate this now in one big system. One person guesses 5, another one guesses 5. Any other guesses? So if I have a state that refers to both systems as one large system, I need to reflect the state of the first system and the second system. But I'm not just adding 2 systems, I'm joining them into one big system. So do you still think it's 5 states or, 5 positions or a different number? So one student guessed it's 6, and that's correct, and we will later explore also why that's the case. But we have some distribution in the first system and then some other distribution in the other system. So actually it's a multiplication in terms of the entries. But we will see in a few minutes why. So if I have some example state of the composite system, I'm putting some comments there. Before we've put there 0, 1, 2, and so forth. But it isn't that easy because I can be with the one system in 0 and within the other system in either A or B. So these comments are now referring to the aggregate 0A, 0B, 1A and 1B, 2A and 2b. And I'm just putting in some probabilistic values in here that are just coming from one example. So 1 divided by 18, 0, then 2 divided by 18, 1/3, and 0.5. And finally, this 1 divided by 18, 2 divided by 18, 1/3 and 1/2, it will just add up to 1. So this is a valid state. And what does that mean? If we have before we had we thought about that one marble that kept moving through our probabilistic system. So what does 0a actually mean from an interpretation? That means there is a chance of 1 divided by 18 that we have our marble in 0 in the first system and the other marble in the other system in A. And there's a 0% chance that my marble is in the first system in 0 and in the second system in B, and so forth. So this is how you need to interpret this. So 2 systems that I combine with 3 and 2 states will lead to 6 states. Sorry, not states, like 3 nodes and 2 nodes. We need a product. So 6 nodes would be, and we will soon see how we can visualize such a joint system. And eventually the number of entries a state has is the product of the vertices. Now we will switch to my slides. We have just looked at these 2 systems and we built the composite system now. We've seen one example state here. Now, how do I actually build such a composite system? For example, I have this 0 and 1. So I want to transition not anymore from 0 to 1, but for example, from 0a to 1a, from 0b to 1a, from 0a to 1b, and from 0b to 1b. And how do I build this? Actually, it's fairly easy. So I have a transition from 0 to 1. The probability is 1/3. I have a transition from A to B, which is 2/3. I have a transition from B to A. So in order to get from 0A to 1A, I need to multiply the probability from 0 to 1 and from A to B. And I do this step by step. So this is written here just in a bit more formal, that I have, for example, the probability would be then 1/3 times 2/3, which would be 2/9 for one specific example. So to get from ij to I prime, j prime, I would need to look up the individual transition matrices and multiply these 2 entries. So this is just a multiplication. This is a very formal definition. And if I try to build this step by step, it will probably take me quite some time because I need to look up these probabilities and in the table and try to multiply them or look into these graphs. And I really hope I don't miss anything. It turns out this is fairly easy to do. And we can do this dynamics super easy by calculating the tensor product. Who of you remembers the tensor product from last week? Send me some reaction if you remember the tensor product, or also if you don't remember it, that's fine. I will just jump back. Last week we introduced the tensor product. I'm just switching there, which was this one here. And we said we have this matrix, and the tensor product would be something like a 2 times 2 times, or the tensor product of a 2 times 2 and a 2 times 2 matrix would be a 4 times 4 matrix. And we build this blockwise. So we say the first four entries in the upper left would be A11 times individually or element wise these entries. Then I have the first four entries up here and so forth. So I guess this rings a bell because we did that last week. And now we see what we actually need it for. Because I want to calculate, or I want to build a composite system now. And rather than manually looking up in the graph and trying to multiply the stuff, I can just do a more structured approach, which is the tensor product. And we have an example here. So I have my matrices M and N from before. M and N were for these graphs, the corresponding matrices, and I can just calculate the tensor product. And the tensor product is fairly easy. We've seen this. So we have M here, which is a 0, and we have N here, which is 4 entries, 2 times 2. So the first 4 entries in the upper left will be just 0 because I multiply 0 with that matrix. And I just continue this with the other entries. So for example, it was 1/6 for M in the upper middle, and I calculate 1/6 times or times each of those entries in N. So we did the tensor product last week, and obviously you're most welcome to test this at home for matrices M and N and multiply the element times every element in the second matrix. And this is super easy to do, so you don't need to look up the graphs and maybe mix up two probabilities, but rather you just apply the tensor product. And the question is here, how do you decide the order of the tensor product? This doesn't matter here so far. You could also have n times, or the tensor product of n and m. It would look different, obviously, because this is not commutative, and also the commons would change. So you would say, for example, A0, A1, and then B0, B1, or whatever, or you would see this. So feel free to try the tensor product at home. For the order, this is something you will see when we actually get to computations, because then there's a proper order we need to follow. And this depends on what the quantum circuit looks like that we are building. So when we aggregate multiple operations, but that's something we will probably see in 2 weeks' time when we look at quantum circuits and we establish operations in such a circuit. Then based on the circuit that we want to build, we would see in which order we would combine them. But for now, this doesn't matter yet. For now, you could also say the tensor product of n and m, but then you would get a different result. The matrix or the elements would be placed elsewhere. And you would also, these comments here, they are optional, but these comments will always be super helpful from now on. So we know what each entry stands for. And then it would be A0, A1, A2, and then B1, B0, B1, B2. So the ordering would also be different. But feel free to calculate this tensor product at home and change the order of n and m, and you get a different one. Because I told you the workload of this course is quite heavy. We do this lecture 3 hours a week, and you're supposed to spend way more on revision, preparing, also your seminar presentation, which is a topic we'll get back to in a couple of weeks. But for now, we're just establishing the mathematics. And then we have this composite system here. So we have this 6 times 6 matrix, and you can try to visualize it. There's already part of this visualization here of this composite system, but your task at home would also be to take this one, look at the matrix from the page before, and complete this visualization. because you have all these 6 entries already in 0A, 0B, 1A, 1B, 2A, 2B, but some transitions are missing. So you would just add the transitions, but you can just read them out from here because you see 0A would have 4 incoming edges from 1A, 1B, 2A, and 2B. And 0A so far only has 1 incoming edge from 1A. So there are more incoming edges for 0A and for some of the others as well. And potentially also more loops. So you would have a loop in 1A and 1B. So you can see the loop in 1A is already in, but the loop in 1B is missing. So this would be one of your homework to complete. Calculate the tensor product on your own. Also try to flip M and N and see what the outcome is and visualize this. When we will discuss quantum mechanics in greater detail already next week, in fact, we will also see something super interesting because when we build this composite system here, we have these composite states and we have these transitions, how to get from, or not composite states, composite positions. And we see how we can evolve from one state to another one. But it turns out there are more states in certain quantum systems, and these states cannot be described through the tensor product. So there are more states that you could think about, and they cannot be described by the tensor product. And that's something we call entanglement. If you've taken physics in high school, maybe you heard about the entanglement in German, that's Verschränkung or Quantenverschränkung, so quantum entanglement. And that's something, it's a very spooky concept from a physics perspective, and we won't be able to discuss this in detail from physics, but we will see it, and it's a concept we will exploit for computing, and it's something quite obscure. So there are states that we cannot describe through the tensor product, but they are actually valid states, and these are super interesting ones, so-called entangled states, and that's something we will discuss next week. Concretely, next week, we will dive deeper into quantum theory. We will see states in greater detail. We will discuss the superposition. We'll look a little bit into observables. We will look into how we can measure a quantum state. Then we see how quantum states can evolve. For this, we need the unitary matrices. We've already got some view into this. And today, at the end of today's lecture, we have assembled probabilistic systems. We will also assemble quantum systems next week, and then we will see this concept entanglement that I have just motivated. Next week will be, again, quite heavy in terms of math. We will discuss some physics concepts, at least the ones we absolutely need in order to do useful quantum computing. It won't be a physics course next week because I'm also not a physicist, but we just look at the physics we need to actually understand quantum computing better. We will look at states and all of these concepts from a very generic perspective. You won't, or you will only be able to understand all of this in a useful way if you're familiar with the stuff we have done today. Remember, the goal is quantum systems, so we established a mechanism and we got step by step more complex. And probably if you do the revision, there will be still some open questions around quantum systems, and that's fine because we will go deeper into the quantum theory next week. After next week, we have established all the foundations we need. So in 2 weeks, we'll be able to look into how we can actually exploit these concepts for computations. And I said next week, when we look into quantum theory, we look at that from a very generic perspective, so very complex states and so forth. And once we have understood this, we will actually have much simpler states, which are just qubits, which are just 0 and 1. with some proportion. And then we build larger circuits of multiple qubits, and we will need all this math again. And once we know how to build this stuff, so with architecture, we'll be busy in 2 and in 3 weeks. After that, we can look into algorithms, theoretical foundations, how to build quantum computers and how to program them. So far, I'm very happy. We have evolved quite a lot with the theory, but please do a revision. Otherwise, you get lost next week when we dive deeper into quantum theory. And then as of in 2 weeks, we will focus more on computing because we have established all the foundations then. And today you saw what math is important for, like the unitary matrices, vectors, and how it all interconnects so we can build these systems. And the systems will be much simpler in the future because we will just have qubits 0 and 1, and we will build aggregate systems or composite systems from many qubits. So we will have lots of simple systems that we interconnect into more complex ones. So that's the roadmap for the next few weeks. I hope you've enjoyed this, spent enough time on the revision, and I will see you next week and have a good weekend. Bye bye.